assignment 12, are they the same questions? You mean the expelled?
Oh yeah, it's 12.
All right, let me just check to see what it is. If that's the case. All right, yeah, I should put up an assignment for that one. Evidently, the title's not the same. Yeah, cool. Keep yourself 5 points for being aware. All right, so I'll change that. I'll get you guys the real assignment on that one, because that stuff is, these things are important right now in terms of the conclusion of the lecture. All right, guys. I put up the lectures from last night. I'll repeat the same thing because this stuff tonight, and I'll do the same thing tomorrow as well. Because these concepts are really weird. You may have to go back and then think about them a little bit for things to really, really make sense. All right, so semi-classical quantum theory, just open this one up. All right, and then it should take you to here, semi-classical. All right, so I'm going to be testing you on the stuff that you guys are looking at. 3 formulas summarizing everything that we discussed yesterday. The first one is known as the Balmer's equation. Let's focus on it. So how many spectral lines generated by the hydrogen atom? We got 4, right? So 4 spectral lines, 4 different frequencies, 4 different colors. So you got red, you got the combination of blue, green, and you got two shades of violet. That's what we got. All right, what does N represent in this formula? The N represents a number. If it's 3, it's going to be red. 4, it's going to be blue, green. 5 and 6 will be 2 shades of violet. So black body radiation law, simply stated, when things are heated, they will glow. When you increase the temperature, color is going to shift from red to blue. That's what it means. So what did Planck discover? Planck discovered that the energy is quantized. Okay, so this is the formula that you're looking at. Energy quantized means that you take the frequency and then you just chunk it out. You quantize it. You turn it into a little particle of energy particle, or energy chunk that you're looking at. So he discovered that the energy is quantized, and based upon that assumption, he was able to explain black body radiation. All right, so what's photoelectric effect? Photoelectric effect is energizing electrons from metal surfaces so that the high energy electrons jump out of metal surfaces using light. So the photoelectric effect is generating current from metal surfaces using light. So you shine a light onto a metal surface, the electrons will come out jumping. All right, if you're using red light, you get a certain amount of current. If you're using blue light, you're going to end up getting a lot more current, which means that the electrons are moving much faster. That's what it means. All right, so what's the Einstein's theory of the photoelectric effect? It's described by this formula. What that simply means is that the electrons will absorb light. The quantized light, the quantized energy, which means that the light is a particle. So which means that the electrons will become energized by absorbing light. That's the premise of the photoelectric effect. All right, so the electrons absorb light, particles of light become energized and jump out of the metal. All right, so which electrons move faster? The ones ejected by blue light or red light? Blue light is higher energy, higher frequency, higher energy. So the blue light electrons are going to be moving much faster. Intensity of light is related to the number of photons, or the light particles that you have. So which electrons move faster? The ones ejected by blue light or dim blue light, bright blue light or dim blue light? How fast they move only depends on the frequency, which is this. Blue is blue. Blue light has a blue light frequency, so dim or bright makes no difference. How fast the electrons move only depends on the color, not the brightness. All right, so which electrons move faster? The ones ejected by blue light, dim blue light or bright blue light? It's the same. All right, does the intensity of light have any effect on the kinetic energy of the photoelectrons? Not really. All right, so the intensity doesn't matter. What did Einstein's explanation about the photoelectric effect prove regarding the nature of light? Light is a particle. That's it. Energy is quantized, which means that light is a particle. So if that's the case, what's the nature of light? Composed of particles or waves? Well, depends on the experiment. All right, depends on the experiment. If it's photoelectric effect, it's definitely a particle. If it's black body radiation, it's definitely a particle. If it's a double slit experiment, it's definitely a wave. If it's polarization, it's definitely a wave. So it's got a dual nature. That's what it means. It's got a dual nature. All right, so moving forward, what did J.J. Thomson discover? What's the nature of electron according to J.J. Thomson? What's the definition of ionization energy, and blah, blah, blah. All right, so let's jump in. All right, so why does light slow down in optically denser media like glass or water or diamond? White light is going to break down into its color components, right? Red on top, the blue is at the bottom. What that means is that the red is moving faster through the material than the blue. So why does the color red move faster than blue? If you change your light source to hydrogen, you're going to end up getting 4 spectral lines, which means that you will get 4 different colors. So where do we get those colors from? Sky is blue because blue light gets scattered more than any other color by the molecules making up the atmosphere. So why blue light? Why not any other color? What's so special about blue light that gets scattered? All right, unputting model is not something I'm going to get into. All right, this is one of the people that I want you to recognize. His name is J.J. Thomson. And as the name implicates or indicates, he's not. He's not German. This guy's British. He was doing a simple experiment at years 1895. What looks like blue light is evidently very sensitive to the magnetic field. So there's a deflection. Only thing that gets deflected are the charges. By looking at the degree of deflection, you notice that whatever's making up the blue light is composed of negative charges. All right, these negative charges today known as electrons. So this is how the electron got discovered. It's 1897, the discovery of the electrons, and for which he wins the Nobel Prize in 1906. All right, so this is the guy who discovers the electrons. What you guys are looking at is known as a cathode ray tube that later became the TVs up until 20 years ago. And this is known as an electron beam. So 1906, Joseph John Thomson, J.J. Thomson, discovers the electron. It's a negative charge. We talked about this guy yesterday. His name is Robert Millikan, who ends up proving Einstein's theory about photoelectric effect, right? While he was trying to prove him wrong. He's one of the greatest experimentalists in the world. And he's the first person who was able to measure the charge as well as the mass of an electron. That's what he did. All right. So what do we know about this? So what did J.J. Thomson discover? He discovered the electron. So what's the nature of the electron according to J.J. Thomson? Guys, it's got a measurable charge. It's got a measurable mass. It's known as a particle. It's a point particle. It doesn't have a measurable size. So you can measure its mass. It's very small. You can measure its charge. Once again, it's really small. And it doesn't have a measurable size. You cannot measure the size because you cannot see these particles. All right. No one has seen an electron before. You cannot see it. You know that it's got a size, but it's not a measurable size. So these are known as point particles. All right, question number 15. Let's talk about the atom at this point. All right, so once the electron was discovered and the electron comes out of an atom, so the question is what the atoms look like. What the atoms look like, the modern physics. All right, as far as you guys are concerned, here's what a hydrogen atom looks like. So you will have the positive charge, and you will have the negative charge moving about the positive charge. All right, this is known as the semi-classical model, or Rutherford's model. It's called the planetary model of the atom. It's called the planetary model of the atom because you got the positive charge at the center, it's like the sun, and moving about the positive charge, you got the negative charge or charges, like the planets move around the sun. All right, the atoms are decidedly neutral, which means that you will have equal number of positive and negative charges. So the net charge is going to be 0, so they will add up to 0. All right. A couple of things about the atom that we need to discuss. All right, ionization energy, we will have to discuss that. What defines the size of an atom, and what are the experimental facts concerning the hydrogen atom? Size of an atom is the radius of an atom. All right, so R is going to be the radius of an atom. It's going to be measured in terms of meters. Ionization energy is the amount of energy required to knock an electron out of an atom. All right, so this is called the ionization energy, so that you can knock the electron out of an atom. All right. So ionization energy is the amount of energy required to free an electron out of an atom. So the ionization energy comes in, knocks the electron out of an atom. This is known as the ionization energy. All right. So the experimental facts concerning the hydrogen atom. Hydrogen atom is the simplest atom in physics. And physicists thought that if you could figure out the hydrogen atom, the simplest atom imaginable, you can just generalize it to any other atom. That was the understanding. All right. And that's how the modern physics starts. So they did a bunch of experiments to get a bunch of numbers. Through collision experiments, they figured out the size of the hydrogen atom. They came up with this number, 10 to the minus 10 meters. And instead of using that number 10 to the minus 10, all right, this is called A with that circle on top. This is known as angstrom. This is known as angstrom. All right, it's an atomic unit, which means that the size of a hydrogen atom is half an angstrom, give and take. It's just in half an angstrom. I want you guys to remember these numbers. It's crucial. So what's the size of a hydrogen atom? It's half an angstrom. Now, what's the ionization energy of the hydrogen atom? Ionization energy, once again, is measured to be it's 13.58. It's usually expressed in terms of EV. EV means electron volts. All right, so these are atomic physics units. So experimental facts: the size of an hydrogen atom is going to be half an angstrom, and the ionization energy is 13.58 electron volts. The reason the numbers are important because whenever you come up with a theory, you have to test your theory against experiments. The theory will generate numbers, the experiments will generate numbers. The numbers will have to match. All right, so Rutherford is the guy who came up with this model, the model that you guys are used to. All right, so you got the net positive charge at the center, so that's your nucleus. The electrons are moving about the nucleus at a given distance. If it's the hydrogen atom, that's going to be half an angstrom away.
Now,
and most of this atom, believe it or not, guys, this atom is 99.9999% empty space. All right, we're all made up of atoms, and all of us are 99.999% empty space, despite the fact that the illusion of solidness is there. We're empty space, so the question is,
now,
if we are empty space mostly, which we are, believe it or not,
how can we reconcile that with the?
Why is that we don't go through each other? All right, why is that we don't go through the doors, the solid objects? Why is it that you're not penetrating the chair that you're sitting on right now? All right, so that sounded really obscene, but let's get back to it. Why is it that you're not going through the chair that you're sitting on? Where do we get the illusion of solidness?
The fact that matter is matter, and my hands don't go through one another. Well, that's crazy, because if it's mostly empty space, they should pass right through one another. Well, what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
All right, so the reason why you're not going through the chair that you're sitting on is the following. All right, so you got two hydrogen atoms. One of them is located right here. And I'll place the second one right here, right next to each other. And here's the size of the first one, and here's the size of the second one. All right, so here's a hydrogen atom from your ass, here's a hydrogen atom from the chair. All right, what's going to happen is the like charges will repel. The positive charges will repel each other in the opposite direction, and the negative charges will do the same. So the negative charge here is going to get repelled in this direction, the negative charge here is going to get repelled in that direction. So there's going to be an electrostatic repulsion. What that means is the closest these charges will be able to get to each other is half an angstrom here and half an angstrom here. All right, when you add them up, your ass is going to be hovering about an angstrom above the chair. So you're not going to be able to touch the chair. The only thing you feel is the electrostatic repulsion, guys. You literally go through life without touching anything or without being touched by anything. It's impossible. That's just an illusion. All right, so the next time when you're feeling lonely, it's the brain's realization that you are really lonely. That's how life is. All right, so there's absolutely no contact between you and anything else. All right, the only thing you got the sensation of contact. And you got the electrostatic repulsion. It's going to fire the nerve endings, this and that. Because of the electrostatic repulsion, you can't go through things. It's going to create the illusion of solidness.
Electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now this means that I'm not really sitting in this chair at all. The atoms in my body are about 1 angstrom hovering over the atoms of this chair. Now,
told you. All right, so we got a problem. The problem is
Rutherford's conception of the atom is a breakthrough.
Rutherford is this guy. This is the guy who gave us the planetary model.
But almost immediately, he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second.
What's wrong with this model?
That's a very secure prediction of classical physics. And that's catastrophic.
Well, you can tell that this guy's an expert in this field. He got all excited. I bet you that he's got a boner going on.
What it's telling you is that atoms can't exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with large volumes that they have.
He just lost it. All right, so here's what he's talking about. Damn, the model that the planetary model wouldn't work. The reason is because we remember the electromagnetic waves. What generates electromagnetic waves, guys? Accelerating charges do. Circular motion is acceleration. All right, so if an electron is circulating around the nucleus, it would lose all of its energy within a fraction of a second. This is like 100 millionth of a second. This thing would collapse into the nucleus. All right, the atoms cannot exist. The electrons cannot move about the nucleus like the way the planets do of the sun. All right, it's just this model is completely false. Rutherford comes up with this model, and then evidently the press gets a hold of it, and then that's it. This is the model that everybody has been thinking about forever. I mean, you guys think that the planetary model represents reality. It doesn't. So physicists a couple of weeks later discovered that that's not the model to use, obviously, and then they forgot to notify the press. So that's the model that you guys think that we use in physics. That model doesn't work. It's not a self-sustaining model. So given the fact that the planetary model does not work, the question is, what do we use in physics now?